Hey guys, this video is for chapter 10. I'm going to explain section 10.1 right here on pages 1 to 8 of this packet. In order to speed things up a little bit, I'll try to mostly focus on the examples and the calculations. But remember, I gave you the big idea that in section 10.1, we're going to have data on a categorical variable broken down into categories. And when we break that into categories where there's 3 or more, we can no longer do a test concerning one proportion or two proportions. So in order to see if 3 or more categories fit according to some claimed set of percentages, we're going to have a chi-square goodness of fit test. And then in the second section, I'll make a separate video for. These formulas, although they are worked out in the notes, they are challenging to work with, a little bit tedious, so I'm mostly going to focus, like I said, on the graph and calculator shortcuts. First big idea, and an example that's going to go through about the first 3 to 4 pages, is, well, what's the scenario? What's the big statistical problem solving that we're doing here? And the idea is that we've got some sort of multinomial experiment, simply meaning we perform a trial, we have n individuals who essentially take a survey, and we ask them a question. It's not a yes-no question anymore. It's not a binomial situation anymore. It's a multinomial situation because we're allowing people to answer in K, mutually exclusive categories. So if we ask you, well, how do you do your taxes? We might ask you to answer by accountant, by hand, by computer software, by friends and family. We're using a tax prep service, and we might have a set of percentages that we believe are true about the breakdowns for these categories. So the null hypothesis will be that these percentages as broken down are true, meaning they're as specified, while the alternative hypothesis will simply be that they're not as specified. So the HO and the HA will have a claimed set of percentages and then simply a statement that the tax prep methods differ from what's claimed. We're going to run something known as the chi-square goodness of fit test, and for that we're going to calculate observed frequencies. Those come from the survey, where we simply count how many people answered within each of the categories. And then we're going to get something called expected frequencies. Well, these are also it's simple math, where all we're going to do is take the number of people we surveyed, n, and multiply by the proportion we believe should be in that category based on the model laid out in the null hypothesis. So here's the survey of 300 people who told us how they did their accounting. How they did their taxes. And there's the 5 categories, and there's how many people said each one of these. Now, these are considered mutually exclusive categories. You can't say, well, sometimes I do it by accountant, and sometimes I use my own computer software. You have to just pick one method for how you do your taxes. So that list of 5 numbers are known as the observed frequencies. And then over here is the math of calculating the expected frequencies. So in pink, all we did was take the 5 percentages in the model, the so-called model that fits the claim, and we multiply by the sample size n of 300, and we get 5 new numbers called the expected frequencies. So you'll notice that these do differ by a bit, some more than others, and the job of a statistical test is to see if these are similar enough to fail to reject the claim, or are they different enough to reject the claim? So what does that for us is this chi-square goodness of fit test. There's 2 conditions to be checked. You should check that you have a random sample and that all of the expected frequencies come out greater than 5. We don't care about the observed frequencies. We could essentially have nobody who answers that they use friends and family and have a 0 here, but we need all of these numbers on this side to be at least 5 for this to be a valid statistical test. So if we check those conditions, the way we crunch the data is we compare every O and E. We take those values, square it, standardize back by E, add it all up, and we get a statistic known as the chi-square statistic. So the chi-square, as I showed you, is always a right-tailed distribution. In fact, it's a skewed right distribution, and we do a right-tailed test always. On page 5 here, I've laid out all of the steps for you. I'm not going to read them out one by one. We'll just demonstrate them in the first example. So if step 1 is to compute the expected frequencies, you take the 5 categories, you take the sample size times the hypothesized percentages, and you get a set of expected values. Well, now I can check the conditions that I did utilize a random sample, and each expected count came out at least 5. HO and HA, I don't really have any way to shorten this. These long sentences here for step 3. There's a claim about the distribution of tax prep methods being 25% by accountant, etc., etc. And then when I write the alternative, the distribution of tax prep methods differs from claimed. Apparently, based on the stem of the question, it says test whether the distribution is different. So to me, it sounded like they're testing with HA being the claim. Right, now I didn't show the chi-square math at all here. I'm going to demonstrate the calculator shortcuts because I'm sure that's what you guys would be interested in. Steps 4 and 5 are simple. I'm just repeating the alpha level for the test and the degrees of freedom, not from sample size -1, but from categories take away 1, 5 categories take away 1, leaves us 4 degrees of freedom. So let's see where these numbers in black came from. I would go in my calculator stat editor, type the 5 numbers for list 1 as the observed frequencies, these 5 numbers in list 2, and then stat test option D. So I've done the data typing already. Stat tests. It's quicker to use the up arrow to get to letter D. D says chi-square GOF test. That's for goodness of fit. Letter C, which just says chi-square test, we'll use that in the next section, 10.2. Once I click here, it's expecting me already to have created those 2 lists. To tell it how many degrees of freedom, it's already on 4. If that's not 4 on your calculator, change it. Calculate and out comes chi-square. So I need that 35.12 for chi-square, and notice my p-value is super small. Don't miss the e-7 on the end. So 4.39 e-7 is essentially 0. So because 0 is less than 0.01, we reject HO. And the number 9, there is enough evidence to support the claim that the distribution of tax prep methods differs from the claimed distribution. Okay, second example, if these are sounding familiar, it's because you sat through a Google Meet and we worked on these in the Google Meet as well. So if I do the M&M problem, there's a claim from the M&M Mars company that the different colors in the bag of dark chocolate M&Ms are uniformly distributed. I decide to test this claim. I get my own sample of 500 pieces of M&Ms. I count how many of each color I get. And now I have a question to do the chi-square goodness of fit test to test the claimed or expected distribution. And what do I conclude? Okay, so I have the observed counts. The step 1 is to get the expected counts. So this phrase, uniformly distributed, I wrote in red down here. Colors would be equally likely, so each proportion should be 1/6. So if I have 500 bags, 1/6 of each color, because there are 6 colors, each a 1/6, that comes out to 83.3. I did have a random sample. I do have each expected count at least 5. How do I phrase HO and HA? In words. The 6 colors are uniformly distributed, and HA, the 6 colors are not uniformly distributed. Alpha's 0.10, degrees of freedom k-1, so I get 5, and let's show you 6 and 7. So if we work this out, we first get into the stat editor, clear out the previous problem, put 2 new lists in. List 1 is the observed counts, that's from the data, counting out those M&Ms, how many of each color. So I make myself a list of the observed counts here. All right, that's the observed counts. And then get myself into list 2, and I put the expected counts in. They're all 83.3. So I'm just going to type that same number 6 separate times. Okay, hopefully you're taking your calculator out and following along. Back to the stat menu, over to tests, up to letter D. Chi-square goodness of fit test. Change those degrees of freedom to 5 for this example. Calculate. Okay, so there's my 3.02 test statistic. 0.6978. Here I have 6973. I probably might have typed in the repeating threes some other time, but anyway, we clearly see it's a large p-value, bigger than 0.10, so we fail to reject HO, meaning there's not enough evidence. Look at HO, we have that as the claim, so it's to reject the claim that the 6 colors are uniformly distributed. So we were believing the M&M Mars that they roughly put the same amount of every color of M&M in the bag. Okay, and then there's 2 extra practice problems that you'll find on pages 7 and 8. Just so that I could do textbook work. Remember, I've asked you not to follow the A, B, C, D, E instructions, but to rather map it out like I've had with the 9-step recipe that uses p-values. All of you who are still getting critical values in rejection regions, I'm asking you not to do that. I'm asking you to base your work using technology and p-values. So what might be different about problem here now is a variation of telling you how many cups of coffee Americans drink, but it's in a pictograph. So essentially we've told you we've broken coffee drinkers down into 5 categories: those who drink 0, 1, 2, 3, or 4 or more cups. We take a survey of 1,600 people. We find this many drinking this many cups of coffee. And now we're going to run the chi-square goodness of fit to see if our survey results matched the distribution of American coffee drinkers. So step 1, the expected counts. Step 2, random sample, each count is at least 5. Step 3, the long sentence with the set of claimed percentages. HA, the distribution of coffee consumed, differs from the claimed distribution, and then it's easy from there. Alpha's 0.05, degrees of freedom 4, the work in red from my calculator. I think showing you 2 examples is enough. You could practice these, make sure you get them. Large p-value, failed to reject HO, not enough evidence to reject the claim. Final example, again, that phrase uniformly distributed. So if I want to know, hey, I wonder if the same proportion of babies are born every day of the week, then uniformly distributed would mean each day would occur 1/7 of the time. So in a simple scenario of you giving me 700 births to look at, and you went and counted how many were born on each day of the week, it looks like Saturday, Sunday seem to be kind of less, which makes sense. Doctors don't like to work on Saturdays, Sundays, so all those C-section mamas are going to be in the hospital scheduled for Monday to Friday. So we see the expected counts. They're all 100. We go with the claim of uniformly distributed in HO, not uniformly distributed in HA. We got a really low p-value, so now we're rejecting HO, and we have statistically shown is enough evidence to reject that claim that births are uniformly distributed. That makes real life sense, again, because there's going to be less babies born on weekends. If you count the scheduled C-section surgeries, it's more likely to put those baby births on weekdays. So that makes real life sense. So pages 1 to 8, you have to work on homework 1, due on Wednesday, May 8th. Sorry, Friday, May 8th. That's it. Section 1's done.